Hey guys, Mr. Bowman here. We have two learning objectives for today and tomorrow, and they are in white and orange. We are learning to describe the features of exponential graphs. So that's going to be the focus of today's lesson. And all of those features will help us with the orange learning objective, and that is we are learning to determine the equation of a given exponential graph. So like all the other graphs we have, we've been given a formula, and that's in green on the right hand side of our screen, and you'll be given a graph, and you'll need to be able to look and identify and describe the features of those graphs, and from those graphs or those features you'll need to determine what the equation of that exponential graph is. And in our internal, you'll also need to practice using your domain and range skills to kind of limit the graph. You don't want the whole graph all the time, but you might want portions of that graph. So what I'm going to do is I'm quickly going to switch to Desmos just to introduce exponential graphs, and then we're going to get back into this question where we will describe the features and link the features to that formula where we'll be able to determine the graph's equation. Hey guys, I'm back and we are on Desmos at the moment, and that formula in green from the previous slide I've written up here. It doesn't really show a graph because there's no numbers in there, but let's start exploring exponential graphs. So just like a parabola, so the default parabola is x squared and it looks like this, and we use that vertex, that point 0, 0, to move the parabola left and right. And we can do the same with cubics. The default exponential graph is the opposite way around. It's 2 to the power of x as opposed to x squared. And there are a couple features of this graph that we need to memorize, or we need to understand in quite a lot of detail, and that helps us with our formula. So the first one is an asymptote. We learned about asymptotes for hyperboles, and this time around there's only going to be one horizontal asymptote, and for the default graph 2 to the power of x, you'll find this graph never becomes negative. The more and more I zoom across, the closer it gets to 0, but it never actually gets to 0. So that is the first hyperbole, or the first feature of a graph that's really useful, and that's the starting point I always find out. First thing I want to do is I want to look and identify the hyperbole. And the next point I want to note is the initial y-intercept. So we can have a look at that. The initial y-intercept is 1. And that is because if you think of our equation, the x value would be 0, 2 to the power of 0, that's going to be 1. If I change this to y equals 4 to the power of x, we'll see again it crosses that spot 1, because anything to the power of 0 is 1. And let's do 100,000 to the power of x, some huge number, and again it crosses that spot 1. So that's a really important point to identify, and the way I normally identify it is I find the asymptote, and that value is always, it's going to be somewhere 1 above that asymptote. And that feature is useful, particularly if it's been moved left or right. You'll be able to find that reference point quite easily. So let's get rid of that. So two things we learned there. The y-intercept at 1, really important feature, and the asymptote, also a really important feature. So let's get rid of those. We're back to our default graph. Let's see the two other features that I want us to look at. So the first one is we can move these graphs up and down just like we do our parabolas and our cubics. So if we write +1, that graph, you can see it's been shifted up 1. So that reference point 1, so what it's done is 2 to the power of 0 is 1, and it's added 1, so it's moved that up to 2. And again, you'll be able to find, if you have a look across at the asymptote has now been moved up 1. So if you found the asymptote, you'd be going, oh yep, the asymptote 1, that means it's been moved up 1 because that should be 0. And if you go up 1 from that, you'll find your reference point as well. And we could also move them down 2 to the power of x minus 2. And we can see that's been moved down. So the asymptote is now been moved down to minus 2. And we moved 2 from our reference point of 1. So it's gone down 1, 2 to get to negative 1. So that's how we move our parabolas up and down. The next feature I want us to look at, just like cubics or just like parabolas, we can move things left and right. And we do that by the bracket component, the x plus b. And again, very similar to parabolas, the b, it's the negative value. So if you want to move it to the negatives, that's positive 2. And if you want to move it to the positives, that's negative 2. So let's have a look. Let's try to move this red graph across. 2 to the power of, let's say, x plus 1. Hopefully that moves to negatives. Yep. And we can see that reference point here. That's been moved across to negative 1. And we still have our asymptote of negative 1, or positive 1. And that was that feature I was talking about. Above the asymptote, there should be 1. And we've identified the 1 value above the asymptote is actually at negative 1. So we can identify that it's been moved across 1. And then let's move it over to positive 2, which means that b value should be negative 2 to the power of x minus 2. And we can see that's been moved over as well. So again, you would find the asymptote and you would track along the asymptote until you can see where it's exactly 1 unit above the asymptote. And that would be your reference point there. So we moved it up or down and we moved it left or right. The last feature I want us to look at is the idea of growth or decay. So our default one is a growth exponential graph, and we can see that because it's going up, it's growing. And if I use another example, let's say 1.5 to the power of x, we can see that's growing as well. But if that a value becomes a number less than 1, you'll actually see it becomes a decay model. And we can see here 0.99 to the power of x, we can see it's actually going down now. Let's make it more obvious by doing 0.5. There you go. That's gone very, very down. And you'll also notice that's symmetrical of, get rid of that 1.5x, of 2x, because 1.5 is 1/2, and that's the reciprocal of 2. So there's a bit of symmetry that we can use here as well. So that would be a decay model, 0.5x, between 0 and 1, and a growth model, or growth anything above 1. So we've got those. Okay, so we've figured out what the A does, makes it a growth model or a decay model. We figured out what the B does, it moves it left or right. Figured out what the C does, moves it up and down. Let's do a couple of examples on Desmos where that uses all 3. So let's do 3 to the power of x plus 1. We're going to minus 2. So let's see how we can find that reference point for our formula. So the first thing to do is let's have a look at that asymptote. And if we're having a look at the graph, we can see it never quite gets to 2. So we can see that negative 2 value, that would be the C value. And we can see that there up in our formula. Negative 2 and negative 2. The next point there is you need to find the reference point, where is the graph exactly 1 above this asymptote, and that's the reference point, kind of like the vertex, and it lets you move up or down. So let's have a look. 1 here is 2. So let's go y equals negative 2. That's the asymptote. And let's have a look at y equals negative 1 above. And what we can do here is we can clearly see at that point there, that's 1 above, and that's our reference point. So what we can see, that point should be up at over here. So we can see it's been moved down 2, and it's been moved across 1. down to cross 1. And that helps us figure out the b and c values. And just like parabolas and cubics, you would need to identify another point on our graph, substitute that in to solve for a. So hopefully you found this Desmos bit useful. What I'm going to do is I'm going to quickly switch back to PowerPoint so we can work through our example and describe the features of that one, and then hopefully come up with its formula. Okay, hey guys, I'm back. We're on PowerPoint again. We just learned about the exponential graphs on Desmos, and let's use all that knowledge to come up with a formula of this given graph. So the first steps we wanted to do is we wanted to explore the features of our exponential graph to help us then figure out its formula. So first step, let's always find the asymptote. And for us, I'm drawing a line across here. Our asymptote appears to be at positive 1. So our asymptote, y equals 1. And that tells us a lot about the c value, and that means our graph has been increased by 1. And we'll put all these numbers into use later. Let's get a different color pen. Let's click into blue. We now want to figure out how much has it been moved left or right, and that's the shift. So how much has it been moved left or right? And to do that, we follow our asymptote line until we're exactly 1 above that asymptote. Or another way to do it is, so the asymptote's at positive 1, 1 above that is negative 2. So let's draw a line across at, sorry, I said negative 2, I meant positive 2. Let's draw a line along positive 2. And that helps us identify the reference point, which has been moved. So that should be at 0, 1 if it was our normal exponential graph, but it's been shifted by the looks of it up 1 and across 2. So that's been shifted to positive 2, which means that b value is going to be negative 2. And I just want to note, it is important during your internal, you do need to explain all of these concepts to help with your responses. So let's have a look. Let's change pen colors again. So, and the third one, is it growth or decay? This helps us figure out the a value, or gives us a bit of insight into it. And it does look like it's growing. So it's a growth model, which means a should be above 1. So we've looked at the asymptote. We've kind of figured out where the new y-intercept, or where the reference point should be. And we've done that. The last thing I want to mention, it doesn't necessarily help us for our graph, but it is interesting. We need, what would the domain of our graph be? And what would our range be? Carrying on from yesterday. So our range, it looks like all values. So that would be all real values. And our domain, we have an asymptote at 1. It never goes below 1. So that's all values for y that's above 1. Okay. Okay, guys, I've put in my working. Hopefully we can see it clearly. We've started with our formula. We've added in b, which we identified as -2. We've added in c, which we identified as +1. And we then are going to use the point identified, 1, -4, where x is equal to 1 and y is equal to -4. We have substituted that into our equation. We have then simplified that. We've converted a to the power of -1 to 1 divided by a, and we've used our algebra to figure out that a is equal to 2.5. And what that means is our formula is y is equal to 2.5 to the power of x minus 2 plus 1. Hopefully you found this video useful. Let's get into some questions.